Hi, my name is Andrew Bouma. I'm a PhD student at MIT, and I'm going to be talking today about the Diablo Canyon nuclear power plant and how we can integrate nuclear power and large-scale desalination at Diablo Canyon to produce a lot of water without adding any carbon emissions. I'm part of a team of 5 MIT researchers, 3 professors, 2 PhD students, myself, and Quantum. And yeah, today I'm going to be talking about Diablo Canyon. So the Diablo Canyon nuclear power plant produces around 2,200 megawatts of electricity for the grid. And this is a big chunk of California's in-state and carbon-free electricity production, and it's set to permanently and fully shut down in 2025. The reason for that shutdown is because of new intake regulations, and so there's a massive amount of water flowing through this nuclear power plant, around 110 cubic meters a second, and that's shown in several other units here on the left. And this is around 12 times the average water consumption of the Southern Nevada water basin or water area that pulls in water from the Colorado River. And this is also around 12 times the flow of the Charles River. And you can see on the left here, the Charles River flowing in front of my home institution, MIT. So this water flows through the nuclear power plant and it's warmed up by 10 degrees C before it's discharged back into the ocean. And in order to meet this new legislation to protect fish, the nuclear power plant would need to reduce their intake flow by 93% or reduce marine organism impingement and entrainment. So the amount of fish and animals hitting the intake machinery are getting sucked into the intake by 93%. There's a couple different ways to do this. One is by changing the way that the water is pulled through that intake structure. The other would be to go to dry cooling or to some other kind of cooling system. There was a study done by Bechtel that looked at what it would take to implement cooling towers at Diablo Canyon, and that involved essentially blowing up the mountain that you see in the background there to build those cooling towers at a cost of tens of billions of dollars in construction costs and downtime. And so our team looked at this question of whether this is still makes sense in light of the changing situation. So when the plant was, they made the decision to shut everything down in 2018. Since then, there's been a lot of things that might make you rethink this decision. One is the drought that's been ongoing in California. So this is a picture of Lake Oroville last summer, which is behind one of the large power producing dams, and the water level dropped so low that they stopped producing power, which contributed to some of the grid reliability issues that they've had in California over the last several years. And which may continue this summer as well. Things are already not looking great. There's also been a number of serious carbon and land use commitments by the state of California, such as the commitment to go to carbon neutrality by 2045 and to conserve 30% of land and coastal water by 2030 as well. And so rapid expansion of things like solar power would make, especially that land conservation goal, difficult. And so in light of this changing situation, we were asked to reassess the value of Diablo Canyon nuclear power plant. This was part of a larger project undertaken by MIT, Stanford, and a consulting firm, Lucid Catalyst, to look at the value of Diablo Canyon for the electrical grid, the value for water production, which is what the MIT side did, and then the value for hydrogen and producing clean hydrogen at the Diablo Canyon nuclear power plant. And so we produced this report, and I'll be talking more about the water part of that report here today. So the question for the MIT side really is, if California is going to build more desalination, and that's kind of a political question. That's not necessarily just techno-economics. There's a lot of questions about how you value risk and different resources, and there's some environmental questions and a lot of different concerns about where you're going to be sourcing your water. But the question we have is, if you're assuming that more desalination is on the way, is this a good spot to do it? And so that's a question of a techno-economic analysis that we can dig into. And I'm going to show in this presentation two things. One, that we can have significant cost savings by co-locating at Diablo Canyon, and that more broadly, reverse osmosis shows really strong techno-economic coupling with nuclear power plants. And this is interesting. This is not something that's really been shown in the literature previously. Most of the time when people are looking at combining desalination and power production, especially nuclear power, they're looking at using waste heat rather than using electricity, because there is thought to be some better coupling there. But what we show in this presentation is that there's really strong techno-economic coupling for reasons other than the thermodynamics or the power consumption portion of that question. So the first thing we looked at is how much reverse osmosis desalination capacity can Diablo Canyon support. We looked at 4 different options. The smallest option we looked at is the same size as the Carlsbad desalination plant in near San Diego, all the way up to something that's over 15 million cubic meters a day, which is around 15 times bigger than the biggest desalination plant in the world today. The middle 2 options have to do, the reason we chose those, the third option here is what happens if we take all of the seawater coming into the cooler, to cool the nuclear power plant, and send all of that to the RO plant. The second option is kind of the limit of how much water you can send to the reverse osmosis plant while still mixing the discharge, the brine, with the bypass flow, and having that be discharged, the mixed discharge be 2000 ppm in salinity, increase over the ambient concentration. And that's one of the limitations for desalination regulations that I'll touch on briefly in a minute. If we would go all the way to option 4, that would involve taking all of the seawater, adding a second intake to bring even more water to the reverse osmosis plant, and using all of the power from the nuclear power plant to power that desalination plant. And that's how we arrived at option number 4. And so we can look as well at how these options fit in with California's water needs. So one reason that California needs more water, one way we can quantify that, is the Sustainable Groundwater Management Act. And so this is a piece of legislation that requires that all of these groundwater basins become sustainable by 2038 or 2040. And in red are all the groundwater basins that are currently critically overdrafting their groundwater supplies. So they're pulling out much more water than naturally percolates back into that ground. Those groundwater basins are aquifers. And so here's Diablo Canyon on the left here. If we look at how much these places are overdrafting their groundwater, the green area here, the 2 groundwater basins closest, have an overdraft of around 190,000 cubic meters a day. Kern County itself has around 840,000 cubic meters a day of overdraft. We can also look at state and federal water projects that move surface water from north to south, essentially from the Sacramento River or the Delta south to the Central Valley and Southern California. And so there's Diablo Canyon again. And these state and federal projects have shortfalls every year, when you compare the amount of water that they contract that they can supply versus how much they actually deliver. And that shortfall is around 6 million cubic meters a day on average. And so putting all those numbers next to each other, we can look at the Diablo Canyon options are in red, and we can compare those to the freshwater project shortfalls in blue. And we also have here on the left the coastal branch, which is just this little piece of the state water project, the shortfall there. And then the green water the green bars are the annual overdrafts, or the average overdraft of the groundwater shortfalls or overdrafts. And then in the yellow here in the very middle for reference, this conference is in Las Vegas, and this is the this was the 2021 water usage from the Colorado River coming out of Lake Mead. used by Las Vegas, just for reference as well. So the point here being that regardless of what option we would build or whatever size of desalination plant you would choose to build, there are some significant challenges that could be addressed by building desalination at Diablo Canyon. There's a lot of factors that are, in order to do a full techno-economic analysis, there's a lot of factors that we looked at, everything from regulations, plant design, the cost of water, how we're getting that power and transmitting it between the nuclear power plant and the desalination plant, environmental concerns, including things like carbon credits and even jellyfish blocking the intakes, all the way to integrating the nuclear plant and the desalination plant and the effects that the nuclear plant would have on the desalination plant, including for things like elevated water temperatures and that effect on membrane permeability. And then where you would build it, how you would build it, some of the roadblocks to building a desalination plant. And so because of the limited time here, I'm only going to be briefly talking about the intake and outfall and briefly touching on the power costs, distribution and regulations, and how all those things factor into the levelized cost of water, which is really what we're concerned about here. So the intakes are kind of the enabling innovation, the thing that make this possible. Again, on the left here, one option would be to meet this legislation to reduce the intake flow or to reduce the impingement and entrainment depth would be cooling towers. However, the option we looked at was brushed screen intakes. So this is something that's really coming from more of the desalination world. We worked with this company, Intake Screens Incorporated in Sacramento, who design and build these screens. And they're kind of being looked at more in depth in the desalination world right now to meet intake legislation for desalination plants. And they involve having a 1 millimeter mesh, so about the thickness of a credit card. And that is where all that water is flowing through. And with such a small screen, they're able to keep out most of the fish and wildlife and all the way down to the babies and eggs and things like that. And this for desalination plants, they're also limited to a 0.5 foot per second approach velocity. So you have a very low velocity flowing through a very small screen, which helps to keep everything out. And that's also a prime environment for stuff to grow, as you can kind of see on the all the stuff growing on this this installment here on the left. But there's these brushes. There's brushes on the inside and outside of these screens, and the screen rotates against those brushes twice or several times a day, depending on the likelihood for fouling. But screens on both sides to keep those screens clean and to minimize the maintenance costs and to not have to have divers servicing these things all the time, and avoiding some of the complications that come from an airburst intake as well. And so the way that this would be integrated with the nuclear power plant would be to have a number of these intakes around a central intake manifold. And so the water would flow through this intake manifold into the existing intake lagoon, which would be sealed off to kind of keep all of the wildlife out of this intake lagoon. And so then the water would flow through the intake screens, through this tunnel, into the existing intake infrastructure. So no modification of the existing pumps or anything like that. And then the water would flow through the condenser, warming the water before it flows into the desalination plant. There would also be, this integrates really well. We could also have an emergency inlet kind of in this new piece of structure, so that if there are any challenges or damage to the intake or anything like that, you could just open up this emergency inlet and keep water flowing to the nuclear power plant and the desalination plant in case of any emergencies without affecting operation. And so there are, I'll say as well that there are significant cost savings here. The cost of this intake system would be less than $500 million compared to the tens of billions of dollars in shutdown costs and construction costs for cooling towers. And because of the way that this could be constructed, there would be minimal downtime to the nuclear power plant as well. So sharing an outfall can also save a lot of money. The existing outfall just discharges warm water directly to this outfall lagoon. And for a smaller desalination plant, you could just mix that water directly in without having any issues. For larger plants, there are limitations on how saline your brine can be that you're discharging. And so in order to meet this legislation, if you would build one of the largest options, you'd have to do a new diffuser style outfall, which would pump that water at high velocity through these outfall diffusers and help that brine to mix in a really small confined area, and not causing the high salinity, high density brine plumes that sink to the bottom and can cause the death of plants and animals if not designed properly. And so we ran into the issue of how do you begin to spec out or determine the cost of something that's, for the biggest options, 15 times bigger than the biggest desalination plant in the world. And we're very fortunate to be located in Boston, right next to the Deer Island wastewater treatment plant, which just so happens to have the world's largest outfall tunnel and is almost exactly the same size that you'd need to build for the largest desalination option. And so you can see a picture of the wastewater treatment plant on the right and the tunnel being built on the left, and that water is that discharge water is moved 9.5 miles out into the Massachusetts Bay. And so a great analogy here that helped us to understand the costs and what that might look like in practice. And so all of this factors into our custom techno-economic model to project the cost of water. A lot of numbers here, but to kind of break this down, when we look at the direct capital costs, so things like pumps and membranes and pipes and things like that, there's really no benefit to building at Diablo Canyon. You kind of have the best costs of equipment no matter where you build it. So no benefits here. And again, we're comparing the 4 different options we look at to a Carlsbad size plant built somewhere else, not co-located with Diablo Canyon. We also have this, the indirect costs. When we look at those, there's really no benefit of building at Diablo Canyon in particular, but there may be some indirect capital cost benefits of building at very large scale. So for things like design costs, if you go really big, there's economies of scale. The intake and outfall, we see benefits, we see significant cost savings because we're sharing that intake infrastructure and potentially outfall infrastructure with the nuclear power plant, which results in significant cost savings compared to building a desalination plant elsewhere. And then electricity costs, we see significant savings by co-locating as well, essentially reducing the transmission costs and some of the other additional costs that you have when you're moving electricity over long distances. If you're co-locating and able to buy directly from the nuclear power plant, significant electricity cost savings, and that can be a significant portion of the cost of a desalination plant. And so we arrive at the bottom line here, both figuratively and literally. And this bottom line, we see a 50% reduction in the levelized cost of water compared to building a desalination plant elsewhere. And I'll note that this is at the desalination plant outlet, so we still have to worry about transmission. And after an analysis of what it would cost to move that water, we see that approximately anywhere within 100 miles and potentially even beyond, it would still be feasible or more cost effective to build desalination at Diablo Canyon and move that water than to build desalination plants somewhere else and have that transmission line. And so the conclusions from this work, we see a 50% cost of water savings by co-locating. And so this is a significant cost savings. We see that the reverse osmosis plant shows strong coupling with nuclear power, as I mentioned before. So significant cost savings by co-locating your power plant, especially your nuclear power plant and your desalination plant, because of all the water that you need to move through that nuclear power plant. And this is not something that's been previously shown in the literature and was a stronger coupling than we probably would have thought previously. And finally, we see that the techno-economics are only part of the picture. And while this may make a lot of sense techno-economically, in order to actually make this real change, there's a lot of social political aspects that need to be addressed. And so kind of in the aftermath of this, we've started really a broader discussion. We released several reports, and these were picked up in places like the LA Times, CNBC, the San Francisco Chronicle, and there was an open letter released by around 80 different climate scientists urging the governor to keep the nuclear plant open. And we got a tweet agreement from Elon Musk, which was kind of cool. And it's not all positive, though. Nuclear power and desalination are both highly contentious topics in California. And so we were also called Ivory Tower. Academics divorced from the reality of the situation on the ground, which was pretty funny. And kind of the latest development here is that California is now kind of reconsidering, and the governor is reconsidering keeping that plant open, which is a great success for the authors of this report. So thank you to all the co-authors and the people who have worked on this report. Special thanks to all the people on the left who have helped to fund and provide insight and intelligence on this report. The QR code on your right should direct you to the MIT Stanford Joint Report. We also have a journal publication under review at Applied Energy at this time. So thank you for watching this talk, and enjoy the rest of your day.